A lot of leading scientists explain the speed-time dilation with a light clock. Here are some examples. Brian Greene.
Imagine now we have another one of these light clocks, but I'm going to have it in motion. Now what do you notice about that path?
It's much longer.
It's much longer.
Brian Cox.
So Einstein imagines a clock, which is two mirrors, with a light beam bouncing between the two mirrors. And that's a nice clock. Einstein says Maxwell's equations imply that we're to take seriously the notion that we all agree on the speed of light.
Vijay Balasubramanian.
Let's see what happens. All right, here we go. Notice the balls go down and up, but you can see that in the moving clock, you can see by the dotted red line that the ball of light has a longer distance to go down and up, just because the clock is moving.
Really, if Einstein invented this clock, then he is contradicting himself. Now, I will explain you why. The light, as we know, has not mass and momentum. And, according to Einstein, the speed of light is constant in all directions, and regardless of whether it is released from a moving object or a stationary object. So, if we do the same scheme with the mirrors, but we take the upper mirror very high outside the train, and we send the photon to the upper mirror from the flashlight mounted on the ceiling of the train. When the photon bounces off the top mirror and returns to the ground, the train will no longer be there, if the mirror is far enough or if the train is moving fast enough. So for both external and internal observers, the photon will travel in a straight vertical line. Motion of the objects are not changing the trajectory or speed of the photon. Evidence 2. If the bouncing photon experiment proving speed-time dilation, this should work in all directions. So let's put mirrors horizontally in the direction of movement. Let's assume that the train, respectively the mirrors, moves at half the speed of light and the distance between the mirrors is about 300,000 kilometers. So the photon, in stationary train, will arrive 1 second to the other mirror. Initially, the photon, while traveling, will arrive more slowly at the opposite mirror because it'll have to catch up. In the direction of travel, it will take 1.5 seconds, but after reflecting from the mirror, it will only take 0.5 seconds to the initial mirror because it is moving against the direction of the photon by 0.5 speed of light. At the end, the total time will be 2 seconds, same like the stationary train. So, do we have speed-time dilation? Yes, we have, but this is not correct explanation. The phenomenon of the speed-time dilation cannot be explained if we do not consider space-time as a whole. Here is how we can explain this phenomena properly. In figure, we see a two-dimensional picture in time-space where a person stands still, and in the times dimension, sections, he forms a vertical line, h, while the person in the moving car forms the inclined line, L. Formulas for this scheme will be exactly the same as for light clock, but this explanation is the correct one. So Einstein arrives at correct conclusions by the wrong way. The interesting thing is that all physicists do not think about it and repeat this mistake.